Alrighty. Thank you all for coming. So let me introduce myself a little bit. Obviously, everybody knows Polkadot here, and that's why we have a room of people standing. But the project that I'm talking to you about comes out of Ava Labs. So a tiny little bit of background. Ava Labs is a project with very deep tech people. It's coming out of Cornell University. I myself am a PhD there. And it's by some of the same people that have developed Selfish Mining paper, the Bitcoin NG paper, Blockstrat, and so forth. So this group of people is pretty foundational in the crypto space. And so what am I going to be talking to you today about? It's something that kind of reminds us of probably all the way back to 2008 when Satoshi came along. It's a foundational new protocol for blockchain, and it sounds pretty controversial, but of course new things that change the status quo are meant to be controversial. So just bear with me for a moment and I'll explain to you why I think what I'm going to be talking to you about is so exciting. So let's start off with a few blockchain observations. Blockchain is one of those things that needs no introduction at this point. We all know what it is, well, sort of. Depends on who you ask. They're ubiquitous. We've raised billions of dollars in private VC funding and even more in public funding. And just the end of 2017, beginning of 2018, we reached almost $1 trillion in market value. But what is blockchain all about on the technology side, and what does it really mean? It's definitely not about some append-only log that is auditable. That's kind of boring. In fact, we're kind of moving to newer and cooler things, which is what part of this conversation is about today. It's not about proof of work or proof of anything. If you have anybody come to you and say, yeah, I have a new proof of X chain, just run away, because they don't know what they're talking about. Proof of X is just a Sybil control mechanism. It's nothing more. I have proof of work. That's how I secure the Nakamoto consensus. I can have proof of stake. That's how I secure a proof of stake system with stake in it and not mining. What blockchain, the broad word, really means, it's a fundamental shift from a client-server infrastructure that we see today with AWS to a completely disintermediated version that it runs completely trustlessly. We can build non-cooperative games for the first time in a manner that we could never do before. We could not do non-cooperative games, meaning games that we require an entity that kind of sits in the sky and is completely unbiasable. We can with blockchain, or the broad term blockchain, and this gives rise to a whole new set of applications that are really compelling, and they can change society, politics, and economics, of course. But we really want to see blockchain. It's so foundational. It reminds us of almost like a coming of age story, as the internet first started off from a small network of nodes, running across a few universities in the US, to what it is today, this gigantic, I don't even know what to describe its system. It's almost has a life of its own, and it has been completely foundational to our society. Blockchain could be something similar to that. At least that is the dream. It's 2019, almost 10 years. Well, it's actually almost exactly 10 years since Nakamoto introduced his or her paper. And where are we really? And so I want to take you all through a technology perspective, not marketing pitches really. Especially those that are hackers and technologists here will appreciate this talk. I want to take you through blockchain 1.0, the initial sort of 2008 introduction. Blockchain 2.0, which is what I'll call the current set of newest and latest things, and then blockchain 3.0, which is something really exciting. So, blockchain 1.0, it sold us an amazing dream. Again, a dream of disintermediated computation, where we could trustlessly run applications and so on. It was an opportunity for many new startups to completely disrupt the status quo, in finance at least. The bar is very low though. Even if all we do is just change the finance aspect of it, and we create trustworthy solutions to assets and exchanges, that will have solved a whole lot of things and we will have succeeded. Even for that though, unfortunately, the current technology stack cannot get us there. Fundamentally, blockchains in general lack from scale, security, are extremely inefficient. They lack from performance, at a whopping 3 transactions per second in Bitcoin. You can run in the order of several, dozens of dollars per transaction for fees. And user experience problems, although of course user experience problems are a developer problem, not really a systems problem. And this is, the unfortunate data point that backs up what I'm trying to say, that there's so many of these problems, nobody's really adopting blockchain. It's a dismal graph. It gets a lot of people upset, but it is a true graph, and truth often hurts. E-commerce applications are not adopting blockchains simply because blockchain cannot support the kinds of throughputs and performance needs that e-commerce applications need. And this trend, nobody's adopting blockchain, and something needs to be done about this. And then you can say, okay, well, fine. Blockchain was never really meant to be an e-commerce platform. It was meant to be something different. And then I would like for you to specify to me which one of these moving goalposts you're referring to, because we keep changing the narrative to fit the technology every year to say, okay, well, we couldn't do this application because clearly the technology is not there. So maybe this is what blockchain is supposed to be doing. We just keep moving the goalposts, and that's not particularly great. One of my favorite new ones is the store of value narrative. But is store of value really the best thing we can do with Bitcoin? Burn the planet for some measly store of value, store something that's scarce in a digital manner? I mean, we can just do this with stamps, and we used to do this with stamps. I think people still do, or with beetles. These are scarce. You cannot just easily replicate them at scale. These are expensive to produce, and we can all collect these and make them as our store of value. Okay? You can say, okay, well, fine. Maybe store of value is not the best thing. Blockchain is great because it decentralizes even those few transactions per second that we get them in a decentralized manner, which means that it's censorship resistant and so on. Except that it's not. For Ethereum and Bitcoin, we love these guys. Like 99% of the mining power is concentrated amongst 11 and 19 mining pools respectively. And the number of mining pools that are required to do a 51% attack is far smaller. So you can cause all kinds of issues with just a little bit of bribing in both Ethereum and Bitcoin. And in fact, there is a fantastic paper that just came out of my colleague, Phil Dayan at Cornell, that talks about front running in decentralized exchanges and the fundamental problems that come along with these kinds of systems. Why is it not, decentralized? It's just simply because the technology, it was designed, unfortunately, to kind of pool resources together and in a centralized system, basically. Ultimately, blockchain 1.0, Nakamoto and so on, are just completely unsustainable and I would say dystopian in a lot of ways. They burn, the energy equivalent of, several countries. They provide really no store of value just because you're burning electricity. We can all replace it with any other models where we burn some resource constantly and somehow that's store of value. It is not economically sound in any sense. Of course, if you ask hardcore maximalists and Austrian whack flavors, that might be something different, but this is how it is. So blockchain 1.0 is completely insecure, both from a technological perspective and from economical perspective. And we're not the only ones that have obviously noticed this. Blockchain 2.0, which is the latest set of blockchains, have come along and have tried to claim that, listen, blockchain 1.0 is not the greatest thing, maybe, and we should probably replace it with something a little bit better. Except that blockchain 2.0 nowadays, a whole lot of projects that, while we have colleagues in a lot of these projects and, we do appreciate what they're doing, they're just rehashes of idea that, Turing Award winners, Nancy Lynch and Leslie Lamport, have discovered like 30 years ago in the 70s and 80s. These are just classical consensus protocols, basically rehashed with new gift wrap. It's the same thing, and now, we incur the same problems as these protocols. They're incredibly unscalable. They, if people tell you that their PBFT implementation scales to more than like 100 nodes, also run away. It just does not. There's actual limitations to how much these can go. If people tell you 1,000, it's absolutely not. It just cannot do such a thing. And this is because simply they require all-to-all communication. They have n squared, n cubed sort of performance overheads. And furthermore, they're extremely fragile. This is something that, for example, to the credit of Nakamoto, this is something that Bitcoin is not. It's not fragile at all. It's extremely robust, in fact. It requires no identity management. But classical protocols, even if a single node is off in our network view, that can entirely invalidate the security of the system. And that can be disastrous. So you can say, okay, well, this is the best we can do. Let's take these ideas because they provide protocols that are very fast and high performance, and then let's add scaling solutions to them, which really just leads to a hodgepodge of new, protocols that are just kind of like sharding things that have also been known in databases for a long time, but unfortunately, these are extremely complicated, and they also dilute the security of the system. If I have to, shard a bunch of validators and have a pool of them globally, I am diluting the global security of the system into its constituent shards. This is a fundamental limitation. And if I say, okay, well, no, I'm going to have everybody validate eventually all contents and transactions in the system across all shards, then you're not sharded anymore. You are just basically temporarily sharded, and then you have to do a reorganization of the entire system. So you either are sharded and you dilute your security, or you're not sharded, and this is a fundamental limitation. Anybody tells you otherwise, again, run away. So it's not impossible to do so, but it's extremely, extremely hard. And you probably want to think about fundamental new changes in the underlying stack, the technological stack, the layer one consensus protocol itself. And really, for example, why I'm really excited about Polkadot is because Polkadot provides an interoperability platform, which even though I believe there's only one consensus protocol that should win out in the end, and I don't want to, spoil it for you. That's just not a realistic, assumption. There's going to exist many blockchains, and we're going to need an interoperability platform to kind of connect them all together. So, can we do better? And this is where the kind of crux of the talk is. And the answer is yes. I'll go through it very quickly with you at the very high level, the kind of properties that this protocol introduces. It's called Avalanche. It was dropped on IPFS last year. You may have heard of the protocol Avalanche, even though we have found out that the United States and China are very, very separate in their communities, extremely isolated. This is at this point, fairly well-known protocol in the US, absolutely not known in this area, which is why I'm very excited to be talking to you about this protocol today. So it's a protocol that is inspired by epidemic protocols, gossip sort of protocols. And it combines the best approaches of both Nakamoto and classical consensus. It basically introduces best properties from both and combines it into one package. Before I get to how it operates, I just want to give you a brief. I'm not the biggest fan of this slide because it's a marketing slide, and I am not a marketer. I'm a technologist, and so, but it is a helpful slide ultimately, and I would like to share it with you. Nakamoto consensus. What it does really, really well is robustness. It's extremely robust. Even though, let's be clear about one thing, if the network is partitioned, and Bitcoin is a synchronous protocol, not an asynchronous protocol. Anybody tells you otherwise, again, one of the list of things to run away from. Bitcoin is synchronous. If the network is partitioned, you have now a security violation in your protocol. You can have two chains run independently of each other without ever converging. And this is fundamental, disastrous outcome of Bitcoin. So it requires very strong synchronicity. But as long as you have the synchronicity assumption, which is precisely 10 minutes per block, then it's extremely robust. It does not need any sort of notion of identities. You just go into the network and you propose blocks via these hashes by solving these nonces. And they're extremely highly scalable, Nakamoto precisely, because it does not require coordination with anybody else. You just download these blocks from anybody, and then you just create these hashes, and then you send them out in the network, and then somebody will eventually hear about these hashes. You don't have to coordinate with any more people. So in that sense, it's very scalable. But unfortunately, 3 transactions per second. It's extremely slow. It's not lightweight at all. And another property here, this property that people keep forgetting about, quiescent. It is not quiescent. Quiescent means that it never can stop. You can never shut down Bitcoin, because if you ever stop doing hashes, I will come along and rewrite your entire history and do a double spend all the way back to God knows where. So you must always continue operating Bitcoin. It can never stop. It just continues growing in size and burning through oceans. Of course, there's other features that we would like to have, but I'll leave those three for next. And the classical protocols, these have been known for since the 70s and 80s. They have been the way that we have built consensus protocols in the distributed systems community in academia. And they're extremely, extremely fast. And that's because all they do is they operate by simply collecting a bunch of signatures. That's basically it. I propose something, I collect a bunch of signatures, I'm done. As long as certain properties are met. And you don't have to have expensive hashes, expensive coordination, expensive block propagation and so on with very high latencies. So they're very high throughput, but unfortunately because I must talk to everybody in the network and I must collect all the votes, I must coordinate with everybody, this means that it's extremely hard to scale. As it scales, I have to communicate with everybody, and then everybody has to communicate with everybody else, and then I need to be sure that everybody in this room has heard of everybody else, which you can see now this starts blowing up. And so for every decision, there is this recursive call that needs to be done, and it can be very expensive. So they just do not scale. Avalanche, by reducing the probabilistic failure rate to the same as Bitcoin, we have a probability of failure that is not zero, whereas classical is completely zero. We basically gain massively in all of these other properties. We're able to scale, and I'll show you some actual numbers, to tremendous numbers, very high throughput, very low latency and quick to finality, and they're just very also robust. They don't require full knowledge of the membership set in the system. So if a single node is off between us, no problem whatsoever. The system doesn't croak. So let me tell you in just two sentences how it works. It's super simple. Now, of course, I am very highly simplifying this. It is not exactly like this. There's much more complexity to it, but ultimately this is the gist of it. Every node samples some set of nodes in the network that it knows of. It collects those a bunch of votes, and then it changes its own decision based upon what it knows in the network. And everybody does this for some iterated number of rounds, independently of each other, with no synchronization whatsoever. So I actually have this is an actual simulation of a system of one of our core primitives. So initially, the system starts off at half and half. You have 400 nodes, a matrix of 400 nodes. It starts off half and half in blue and orange. So everybody is either colored blue, like in this room. Half of you are colored blue, half of you are colored orange, completely at random. And then you start looking around. I say, okay, these guys are blue, so I'm going to become blue myself. And maybe somebody else look at somebody else, says, okay, these guys are orange, I'm going to become orange, and then we just keep repeating this. And that's basically it. And initially, it's kind of metastable. And as soon as one color gains majority, it immediately falls to that majority, and it gains confidence and stays there. This is a fundamental property that makes Avalanche so strong. It's this ability to, once it goes to majority orange, it's really freaking hard to go back. In fact, there is this probabilistic, the analysis shows that once the system, here, you have some probability of moving to either color, and these lines should be orange and blue, my apologies, but once it goes to all majority orange, some let's say 80% orange, it becomes incredibly unlikely for the system to ever revert back. In fact, the probability of these guys to gain majority is extremely small. It's basically zero. And so the system, the security system relies on the ability for us to go into this irreversible zone and stay there. And we get there with in just a number of rounds. Small number of rounds. Okay, so that's the core primitive. I'm going to get a little bit technical, not too much. The core primitive is very simple, but of course, if you want to build a full consensus protocol, you have to do a bunch of optimizations. And in particular, you want to amortize multiple decisions into one. You don't want to run this core protocol, the little GIF that you guys saw. For every single decision, you actually want to amortize everything together. And the way you do that is through a very simple idea, but turns out to be very, very powerful. And that is you link decisions together by pointers in a DAG. And it's pretty straightforward. So decisions are implicitly mean, if I vote for this transaction right here, for example, this is an actual transaction, Charlie pays Fiona. If I vote for this transaction, it implicitly means also a vote for Alice pays Charlie. And then this one also means an implicit vote for the Genesis block. So there is a transitive voting that happens. But note that unlike some systems that have tried to do DAGs without naming names, they have done it wrong. And the reason is because they take votes into account as part of the structure of the DAG. We don't. You still have to do this query for every single decision. So in fact, if the adversary can come in, introduce a massive sub-DAG here, it wouldn't matter. You would have to still do all these queries one at a time. So the DAG is simple, but it's very powerful because it's naturally sharded. We can work on different parts of the DAG simultaneously in parallel, and there is absolutely zero coordination in the system. So what does this mean? This is an actual implementation on a geo-distributed 20 locations across the globe with 2,000 nodes, full ECDSA signature verification on a network of 125, 250, 500, 1,000, 2,000, doubling for every bar graph, showing the actual throughput. Our bottleneck in this experiment is actually the CPU cycle spent for signature verification. If we were to turn that thing off, this jumps immediately to 16,000. So you can easily parallelize that by using multiple cores, but we just didn't have enough cores. So this is the experiment that we ran. And the latency is extremely low, just basically 1 second. In 1 second, you can send your transaction and get it approved in the network. And in fact, this is for full finality, for very high probability, like confidence in the transaction that it will not be double spent. If you can even wait like sub-second speeds, but then of course you might have some higher probability of a double spend here. So what does this mean for security? The extreme decentralization properties and scalability means that now we can have thousands and millions of participants, like actually not just making up numbers. We can have these kinds of numbers in the network, and this means very high immutability in the system. Rather than have a set of about 4 to 5 mining pools control half the mining of the network, we can now, you'll have to bribe a whole lot of nodes in the network in order for you to do anything in the system, and anything bad. And then one thing that we also provide is that, to our knowledge, we're the only one that does parametrization of the security of the property by allowing the system to extend to more than half Byzantine nodes. And Byzantine meaning adversarial. So you can have more than half the network be corrupt and trying to attack a system, and it will still be safe. Of course, we have some theoretical results that show that this implies some degradation in liveness and performance. And then lastly, because we don't require to sample everybody and vote for everybody in the network, this is a very robust system. You don't need to know everybody in the network. You can actually know a subset of the network and still be totally fine and provide the high security guarantees of like a full network knowledge. So, sorry for the kind of digression in the technology. Now back to a little bit on the platform itself. So, we are a group of researchers out of Cornell. We have been working on this for some time now, but only recently have we started putting this together into an actual platform. So we're a very, very new company. We're very young, but we have big plans, and the people in the team and the founders here, including myself, we've done some foundational work. But the CEO of the company, for example, he is Emin Günsir, foundational in the space. So for the first release of the platform, it's going to be a payments tokenization platform with built-in governance inside. The native token, we have some key innovations here, and I can share some of them with you and not the rest, unfortunately, due to competitiveness in the space. But the native token is what provides the core security of the system. It's you stake in order for you to validate in the system, and you get rewarded for staking and providing security in our system. And we have a token platform. Some of the key innovations here is that we allow arbitrary scripting languages, so you can compose a transaction that spends and understands both Bitcoin and Monero scripts, for example. So you can create arbitrary transactions of this type, and it has a lot of expressibility. And then there's also the one really important innovation that I'm particularly really excited about, and that is the ability of the system to provide value to the native token by taking value from the higher level tokens that are built on the platform. This is a key property that you want in your system. Let me give you an example why this is important. Ethereum ERC20 tokens, they can become potentially much more worth, much more higher market cap than Ethereum itself. and they still wouldn't provide any sort of value to the underlying token holders of Ethereum. The miners of Ethereum are running a system where their tokens are way less worth than an ERC20 running on their system. Now you can say, oh well, that would never happen because you would speculate on the value of Ethereum being higher than the total aggregate of the tokens built on top. That is not the case. It can easily change. In our system, the base security of the system provided by the validators, you must incentivize high security and high decentralization, so you must provide value from the tokens built on top to the underlying native token as well. And of course, governance, this wouldn't be an interesting conversation, I guess, if we didn't talk about governance, because that's a hot topic these days. Governance, we also, the nice thing about governance in Avalanche is that governance is basically just a simple transaction in our system. We already are a crowd oracle. You are sampling people and getting the majority opinion of the network. Effectively, if you want to issue a governance transaction to say, for example, let's change the interest rate or the fees paid out per transaction, you just simply issue a new transaction that says, hey guys, can we change the transaction fees for this particular type of transaction? And then you issue into the network and people will vote on this transaction. And if it passes, great. If it doesn't, so be it. Now, I will very briefly talk about the dApp platform. We're going to be eventually also a dApp platform, of course, but this is for V2. We're going to support in multiple scripting languages, but also multiple VMs. We're going to support the EVM as well as WASM. And of course, we're aiming for much higher throughput and all these things than other chains out there. And we have a fantastic privacy story, which is simply the ability of developers to name a bunch of validators in the system to run their smart contracts without having to share the state of the smart contracts in the entire network. This is a very a similar property as to an offline, a sort of off-chain smart contract. So where are we now? We truly think that this set of protocols are revolutionary in how we are actually going to build consensus protocols, which are foundational, obviously, for blockchains in the near future. Using them, we can, at the very least for finance, we can disrupt it to the kind of levels that we were intending from the very beginning. We are funded by Andreessen Horowitz, Polychain, Metastable Initialized, some of the top, if actually the top funds, both crypto and non-crypto in the US, but are looking very much so to talk to you, especially talented researchers, hackers, technologists in this area of the world, because we really very much value our presence here, and we understand just how valuable this community is. So we would love for you guys to talk to me about developing on our platform, which is to go public soon. And some contact information, and that is it. Thank you.
好，谢谢 Kevin 的分享，然后接下来我们